afternoon. I'm very happy to kick things off. We've already have 100 participants logged in. We have over 350 participants registered, so we expect people to be joining as things progress this afternoon, but we decided to start nevertheless. We have a full program ahead of us. So again, welcome to everyone. This is the next installment of Cogen Europe's Power and Heat Boost webinar series. And today is a special one for us because we'll be presenting the results of a study we commissioned with the consultancy Artelys to look at the role of cogeneration CHP in 2050 and what does that mean. Before I start, just a few housekeeping rules. So, oops, things are moving too fast. All of the attendees that have logged in are muted and have no video. This is just to ensure good sound quality. Please note that this session is being recorded. It will be made available on the Power and Heat Boost segment of the Cogen Europe website, as well as the special section to publish the results of the study, and all participants and those who have registered will receive a link announcing that the recording has been made available. Questions can be taken via the Q&A app. I will let you know when that will start. We do have a specified Q&A session right after the Artelys presentation, so we can collect questions as they come in during the presentation or also during that segment. Next, just a quick overview of all our different speakers. After my introduction, which will end in less than 30 seconds, our chair, Marco Pesagia, will give a brief introduction, followed by Mr. Bertoni from the European Commission, and then we'll have the presentation from Artelys, from Christopher André, and then myself will provide some summary and some concluding remarks and some recommendations. After the Artelys presentation, there'll be a segment for Q&As, and that's when we'll take the questions. So without further ado, I will give the floor to Marco to give his brief introduction. Marco, the floor is yours.
Thank you, Hans. Thank you, everybody, and good afternoon. I am Marco Pezzaglia, the chair of Cogen Europe and the European Association for the Promotion of Cogeneration. It is my pleasure to welcome all of you to today's Power and Heat Boost webinar, where we will present the results of our study assessing the role of cogeneration in achieving a decarbonized energy system in 2050. I'm happy to see many of you connected. This shows a keen interest in cogeneration and its role in the future. Well, to introduce this webinar, I would like to start by saying that in our many exchanges with the European Commission and other EU institutions, our sector has often been asked to demonstrate its contribution to a net zero economy. Well, today, personally, I'm pleased to present you the contribution of our sector to support the EU in achieving carbon neutrality by 2050 at the least cost. In 2018, the cogeneration sector and we as association adopted a new vision for the future. Our sector committed to creating a resilient, decentralized, and carbon neutral European energy system by 2050, with cogeneration and at its backbone. This vision was supported by our 60 members spanning the entire energy value chain. To back up our vision with science-based evidence, Cogen Europe commissioned a study with the well-known consultancy Artelys to demonstrate the role of cogeneration to build a more efficient, integrated, and cost-effective carbon-neutral energy system in 2050. From the point of view of European perspective, with its European Green Deal, Europe is leading the way in meeting the Paris Agreement goals. Being an energy system integration and an energy efficiency solution, the cogeneration or combined heat and power should be at the core of meeting the Green Deal ambition and its various initiatives: renovation wave, industrial strategy, energy system integration, hydrogen strategy, etc. Europe needs higher ambition in renewables and energy efficiency, and our sector can help to deliver these. However, we see that there are not sufficient efforts focused on energy efficiency today. This is especially true for cogeneration, and despite its recognized benefit, there is still untapped potential for cogeneration to double its double its benefit. Yet, in a resource-finite world, we can no longer afford wasting energy. And this is very important, a very important concept that I would like to stress again. We are in a resource-finite world, and we can no longer afford wasting energy. Cogeneration needs to be prioritized over the inefficient separate production of heat and power. This will help maximize energy efficiency in key sectors of the economy and integrate the European energy system at least cost. The future, the next 5 to 10 years, will be critical to drive investments in the right direction. EU policymaking has a key role to play here. The upcoming reviews of the Energy Efficiency Directive, the Renewable Energy Efficiency Directive, but also the Energy Taxation Directive, to cite a few, are key opportunities to prioritize supply-side energy efficiency, foster innovation, and stable support scheme. This is the key to give markets the stability they need to make today the investments they will need, that they will make tomorrow. Running increasingly on renewable energy sources, cogeneration will enable a highly electrified and renewable net zero energy system. On the way to 2050, cogeneration will play a crucial role to make the most out of the fuels of the future, to close the loop of renewable energy in the most efficient way and avoid wasting these valuable resources. Our sector is one of the key ones to make the rest of Europe more resilient, competitive, and sustainable. Well, now to start this workshop, we will have the pleasure to hear from Mr. Guido Bortoni, advisor to the Deputy Director General on Internal Energy Market Regulatory Issues at DG Energy. He will give us an overview of the European Green Deal initiatives and set the scene for our discussion today. Then we will have Mr. Christopher Andrew, Director at Artelys, that will then present the key study findings and recommendations. His presentation will be then followed by an exchange of views with all the webinar participants. Finally, Hans Korteweg, our Cogen Europe's Managing Director, will provide a summary and policy recommendation to close the webinar. Now, let's kick off this webinar on how we can deliver the energy transition together. And let me now give the floor to Mr. Guido Bortoni from DG Energy. So Guido, please, the floor is yours.
Thanks, Marco. Good afternoon, everyone. And thanks to Cogen and Artelys for asking the Commission to open this event for presenting the final result of their study. This is particularly relevant in the context of the Commission Green Deal initiative, where everyone knows our strong commitment to reach carbon neutrality by 2050. Any support also from the study, also coming from the industry, will be key in achieving this ambitious objective. As a way of introducing this workshop, let me start with a very brief overview of the relevant European Green Deal initiatives and highlight some important synergies where we see in particular a role for cogeneration or combined heat and electricity generation. As you all know, the European Green Deal is the #1 political priority of the European Commission. It's our roadmap for making Europe the first climate neutral continent by 2050. It is Europe's new growth strategy as well. As a part of the Green Deal, the European Commission presented last month its climate target plan to reduce EU greenhouse gas emissions by at least 55% by 2030, compared to 1990 levels. This increased level of ambition will put the EU on a balanced pathway to reaching climate neutrality by 2050 and to consistently distribute efforts, decarbonize efforts, across the 3 decades ahead. The impact assessment demonstrates that this course of action is realistic and feasible and prepares the ground for adapting climate and energy policies to help decarbonize the European economy. With such an increase in our climate ambition, the overall decarbonization of the energy system is a priority. You know, we are, let's say, energy is responsible for 75% of GHG emissions. And by means of energy, this will have significant implication in decarbonizing all energy-powered sectors. I mean power, heat, generation, buildings, transport, and industry. In particular, we will need more energy efficiency as per the energy efficiency first principle, as well as more renewable energies into our energy system and the deep penetration of decarbonizing technologies everywhere, also in the hard-to-abate sectors. The energy system integration strategy is the strategic menu which will enable us to transform the current energy system as a whole, linking the various energy carriers. I mean electricity, heat, coal, gas, solid and liquid fuels as well, with each other and with the end-use sectors such as buildings, transport, or industry. Already by nature, cogeneration provides a solution for the energy system integration. With one single input, it generates 2 outputs, translating into physical links between energy carriers, heat, electricity, and gases, and across sectors. So, in short, we have to extend by large what the pioneering integration of cogeneration already does. At the same time, cogeneration offers potential in terms of energy efficiency, reduced CO2, renewable deployment, system efficiency by providing flexibility as well, and grid cost reduction, and of course, energy bills reduction. In this regards, the energy system integration calls on the importance of infrastructure planning, including at local level, in order to facilitate the integration of various energy carriers. This will be relevant also for cogeneration. Besides, as part of the package adopted last week, the Commission presented the renovation wave. The objective is ambitious and straightforward. We want to at least double the annual rate of savings that renovation brings to their entire energy consumption. This means renovating 35 million buildings, this is the objective, public and private, deeper than before by 2030. The renovation wave pays special attention to the heating and cooling sector as it represents much of the energy consumption of buildings, 80% of energy consumed in residential buildings refer to heating and cooling. Therefore, we want to promote efficient and low carbon technology and the use of waste heat and cold, and we will increase the current target for supplying renewable energy to end consumers. Modern district heating systems should also be promoted as they can connect local demand with renewable and waste energy sources, as well as the wider electric and gas grid, contributing to the optimization of supply and demand across energy carriers. Here again, we see large potential for cogeneration to bring benefits for citizens and to contribute to climate neutrality. Cogeneration can also address some limitations of the all-electric model. Indeed, if all heating and cooling is electrified, this will put a strain on the electricity grid, which may not expand rapidly enough over the coming decades to accommodate this enormous growth in demand for electricities. Here, heat in particular, through cogeneration, which allows for the utilization of heat generated when producing electricity, have a key role to play. In the context of the climate target plan and the recently adopted strategies, the Commission will now start preparing detailed legislative proposals on how these ambitious climate and energy targets can be achieved. You know, last Monday 19, the Commission published its work program for 2021, which shows that the months ahead will be particularly busy. The Commission will propose by June 2021 the revision of the Energy Efficiency Directive and of the Renewable Energy Directive. This is now subject to further consultation and analysis. Based on the thorough impact of assessment, such revision will explore a toolbox of measures to promote the decarbonization of heating and cooling and the comprehensive heating and cooling planning. Besides, the Commission will propose the revision of the Energy Taxation Directive in the second quarter 21 to promote a level playing field across all energy carriers. In particular, the Commission identified in the Energy System Integration Strategy, I'm sure you know, that an important barrier in buildings is the relatively higher level of taxes and levies applied to electricity and the lower levels of taxation for fossil fuels used in the heating sector, which leads to a lack of level playing field, should be outplaced. To conclude, this task ahead is challenging, of course, is significant, but necessary if we want to get things right and achieve climate neutrality. We need to adapt consistently, as I said, our climate and energy framework starting from now. For that, we need to base our proposal on a thorough impact assessments, proper modeling, and use of all information and data at our disposal. I therefore thanks Cogen again for contributing to the debate, and I look forward to listening from the study and the debate and the 2 days debate. Thanks a lot.
Thank you, Mr. Bortoni. Thank you for your keynote intervention. I suggest we move to the first presentation. So I'd like to welcome Christopher André from Artelys to give to present the results of the Cogen Europe study. The floor is yours, Christopher. Thank you.
Thank you, Hans, and thank you very much for the invitation to share the results of this study. My name is Christopher André. I'm a project director at Artelys. I will be here also presenting the results of the study and answering the question in the subsequent Q&A session, where my colleague Maxime will also take some questions. In terms of the agenda for this presentation, I have first a short overview of the key objectives of the study. Then I'll present the methodology and results for the two parts of the study. One is called user focus, focusing on the end users, and then the system focus, where we look more deeply at what are the systemic impacts of CHPs. And then I will conclude and provide some recommendations, also in terms of modeling, and then provide answers to potential questions from the audience. So let's begin by a short overview. And here, I think Mr. Bortoni has done an excellent introduction to the study and the context. So of course, it's the key point here is that we are in the context of the European Green Deal. We have an ambition to have a first continent reaching a net zero emissions by 2050 in a cost-efficient and secure way. The different enablers of such transitions The key ones being energy efficiency, energy system integration, as well as the direct and indirect electrification of a number of end users. As also mentioned previously, various policy initiatives are being taken in order to ensure that the EU can achieve these objectives, such as the energy system integration strategy, the hydrogen strategy, the renovation wave that has also been mentioned, and the revision of a number of directives, including energy efficiency and renewables. So in these 2050 worlds, we'll see energy system integration as being the core concept. We'll see a lot of electrification, roles for renewables, a need for flexibility on different timescales, and green gases part of the picture. So one of the key questions is, as we'll have some need for green gases, what is the role for the most efficient technologies available in order to use them in an efficient way and from an energy perspective, but also from a cost perspective. So in terms of background, I think we have covered also via Mr. Bottoni's introduction the key points regarding the context, and what we aim at doing with this study is to pursue three objectives. First is to explore the potential of further integrating Europe's energy system in an efficient way in order to reach carbon neutrality, to assess in this context the role of cogeneration, building on the long-term decarbonization strategy published by the European Commission, and then finally to provide recommendations on how to ensure that we can capture these benefits that we have identified in terms of policymaking, but also in terms of modeling when designing new scenarios for the future. Two quick words on Artelys and who we are. We are a consulting and software edition company. We are specialized in energy system modeling and decision support. And in order to carry out this assignment on behalf of Cogen Europe, we have used the model called Artelys Crystal Supergrid, which has been used with an European-wide integrated gas, heat and electricity scenarios that capture the key aspects of the energy transition, and in particular sector integration and the links between the electricity and heat sectors in particular for this study. So in terms of content, we'll have two separate parts of the presentation. The first one focuses on a number of CHP applications. So here we have looked at the microeconomics of different use cases, where we have compared the performance in terms of costs of various portfolio of technologies in different cases with different heat demand profiles, different technologies, different energy sources. And this, we have repeated this analysis for different countries. So here it's from an end user point of view, whether it makes sense to include CHP in the portfolio of technologies. And we'll see that in all the cases that we have looked at, this is indeed the case, that there are savings from an end user point of view. And then the second step is to adopt a system point of view and look at the benefits of CHP for the energy system, and looking at benefits that go beyond the end user, also in terms of investment and the whole dimensioning of the European system. So I will go through the user focus first, presenting the methodology and key assumptions. And then if there are some questions, I can take some questions on the user focus, and then I'll move on system. So what is the user focus? It's a comparison between two configurations, one including CHP in the portfolio of technologies and one without, in 7 different use cases. The use cases cover different applications in the residential, industrial, and district heating sectors. They differ by their heat demand profiles and the price of energy. Both the situation without CHPs and the characteristics of the CHPs are adapted to the end use. I will show the different end users that we have considered on the next slide. Then we have performed hourly simulations over 1 year in 3 different countries. So here we have Spain, Poland, and Sweden. And the key indicator we have looked at is the cost of heat provision. So how much does it cost per megawatt hour of heat being supplied by their system. So for each use case, we have compared a situation without CHP that we have called the benchmark to a situation with CHP. We have done that for 7 different configurations. I will not go through all the details of this slide, but what is important to see is that we have different type of applications and different technologies. So we have fuel cells, we have gas engines, gas turbines, and combined with different levels of heat storage for different temperature levels in industry, in different applications, also in the residential, hospitals, or district heating. And so for all these 7 use cases, we have designed a benchmark that is an alternative portfolio of technologies without CHP. And then we compare the cost of meeting the demand for heat in both these systems. So here, just a very short example to show you how we have done this. So on the left-hand side, you have the benchmark configuration without CHP, where you have a heating demand in orange on the left-hand side. And then you have a portfolio of technologies, so heat storage, a heat pump, for example, and then boiler. You have the heat pump that interacts with power markets and carbon neutral energy coming into the boiler in this example. And so with this, you can calculate a cost of meeting the demand for the heating. And we compare this with the situation on the right-hand side, where you allow the system to invest in CHPs. And so now you extend the mix of technologies, still can have some heat storage, heat pumps, boilers, but then you have CHP coming in. Still interaction with power markets for the heat pump and for the CHP this time, and carbon neutral energy coming in. And in this case, you can also calculate the cost of heating, where we take into account the benefits provided by the fact that you can sell some of the excess power on the power markets. So if we now move in terms of the key results for the user focus, here I have put some of the key use cases that we have considered in this study. So we found that in all these use cases, installing a CHP can be beneficial to the user from a cost perspective. And this is the case even when you exclude the avoided network tariffs, taxes, and levies that can be saved due to self-consumption of the electricity, for example. The benefits can, of course, vary depending on the use case, on the country we've looked at, on the fuel prices, the technology costs, and different characteristics of the technologies that we have compared. So we have provided a range for the different use cases. So for example, on district heating, on the left-hand side, looking at a consumption of 500 gigawatt hours, you can have savings ranging from 0.4 to 3 million euros, depending on the country where you are or the fuel prices in this country. And then similarly for all the others, we see that for in hospitals, industry, with different temperature levels and different dynamics of the demand, you also reach a situation where the configuration with CHP is the most economical of the 2 alternatives that we have considered. And so this is true for all these end users that we have here on this slide. So this first step of the study has demonstrated that there is potential for CHP to be economical from an end user perspective. So now the question becomes, what are the benefits when considered at the system level? And how does it interact with the rest of the power system in particular? So, and just a word before moving to the second part, as I mentioned, the benefits that we have shown on the previous slide are system level benefits that do not include the additional benefits that end users can capture from avoided taxes and levies and network tariffs. And if we consider the entire consumer bill, CHP can become even more competitive than alternative technologies and in more use cases. And for example, fuel cells are found to be competitive in the residential sector from a final user point of view, in particular in those countries that face high electricity prices in wintertime or a high level of taxes and tariffs. So now that we have seen that indeed CHPs bring benefit to end user, let's see how this translates in terms of system, and in particular in terms of investment, CO2 emission, total costs. So in order to undertake this, this assessment at the system level, what we have done is we have first begun by defining some scenarios. So we have based the analysis on scenarios inspired by the 1.5 tax scenario of the long-term strategy of the European Commission. We've looked at different sectors in terms of heating demand and assessed what is the potential for CHPs in these different sectors. We have calculated what the 1.5 tax scenario of the European Commission has provided for CHP and what is the additional potential where we think CHPs could compete. And then once we have identified the potential at the maximum heat demand that can be covered by CHPs, what we did is to run an economic optimization. And here there is a trade-off between supplying heat and electricity via separate technologies, so pure electricity production technologies, pure heating technologies, or to invest in CHPs and then to have this combined heat and power. So in the configuration with additional CHPs, of course, you have to pay for CapEx, for capital costs, but then you have some savings in terms of fuel costs. So the question becomes, what is the balance between the additional CapEx and the avoided fuel costs? And with this optimization, we install CHPs in the sectors only when they are found to be economical. And then on the right-hand side of this slide, you can see the final step of the study is to compare the results. So here we have drawn some conclusions at the EU level in terms of deployment of the different technologies, the costs, the CO2 emissions, etc. And also we have performed a sectoral analysis of the deployment of CHPs in the different sectors and the share of heating demand that is covered by the different technologies. To perform this, we have used a pan-European heat and power model where we have used our own model, Artelys Crystal Supergrid. So here we have used an hourly time resolution in order to ensure that we can capture the synergies between the periods where you both need heating and electricity from thermal technologies, and to see what is the role of cogeneration to provide both these services at the same time. So the electricity generation assets are aggregated by country for each of them, sometimes aggregated by efficiency classes. The consumption is modeled by sector, with advanced modeling also of flexibility solutions, especially in the electricity system, so electric vehicles, electricity storage, but also heat storage, as I've shown previously. And the model enforces the balance between supply and demand for electricity and heat for each hour in each of the countries. And then the model is able to determine what is the optimal deployment of CHPs or competing technologies in each of the countries. As I mentioned, the analysis is based on the 1.5 tax scenario. So here the first 3 bullet points show you how we are inspired by the 1.5 tax scenario. So the energy consumption, heat supply in each sector, the levels of energy efficiency and electrification are directly adopted from the 1.5 tax scenario. Also, the installed capacities of variable renewables, hydropower, and nuclear are taken from the 1.5 tax scenario. The rest of the electricity generation mix, biomass, biogas, natural gas, hydrogen, is also optimized. And then we have performed this optimization, as I mentioned, with an hourly time resolution, which we believe is very important in order to capture the synergies and the interlinkages that CHP allows to bring between the heating and the electricity sectors, and the country level granularity. And the geographical scope was EU27, the Balkans, Switzerland, Norway, and the UK. We have taken a number of technical constraints into account. Don't want to go into them too much in detail. The final 2 points are interesting also in order to take into account the reduction of grid losses that come with the deployment of CHP and the avoidance of network reinforcements. We have implicitly considered both these aspects, these benefits of CHPs, by adapting efficiencies and capital costs of CHP technologies. And finally, the optimization of CHP deployment is only considered in sectors that are not electrified, meaning that the deployment of heat pumps is not re-optimized. And the goal of the optimization is to minimize total system costs. In terms of scenarios, we have started from we have performed this analysis from 2 starting points. So as I mentioned, the 1.5 tech scenario, here we denote 1.5 tech star. This scenario, because it's not strictly speaking the 1.5 tech scenario, it is our understanding of the 1.5 tech scenario. We have this scenario as the central one in the analysis, and then we have a scenario variant, which is called Integrated Energy Systems, IES, where we have included higher shares of green gases, including power to X and hydrogen. And in both cases, then we have repeated the same analysis. We have done the economic optimization of CHP deployment, and both result in more CHP installed compared to the 1.5 tech scenario, more efficient use of energy and reduced energy costs. So in total, we have 4 scenarios being considered in this study. One baseline of the 1.5 tech scenario, and one 1.5 tech scenario with optimal CHP deployment. And the same thing for the IES scenario, one baseline, and then one optimized CHP deployment scenario. A few words on the 1.5 tech scenario before jumping into the results. So as I mentioned, the 1.5 tech star scenario relies on publicly available assumption of related to these scenarios and pathways shown in the long-term strategy of the European Commission. And I've put here 2 figures that are important in order to understand in what context we are working. So on the left-hand side, you can see the evolution of the power mix at the EU28 level in terms of installed capacity in gigawatts of the different technologies. So you see a drastic increase of the wind onshore, offshore, and solar technologies in particular. Of course, a drastic reduction in fossil fuels. But you see that we have an increase that is very important. And why do we have such increase? Of course, to phase out some of the fossil fuels, but also to supply electricity for indirect electrification of a number of end users. So on the right-hand side, you have the final energy consumption by energy carrier. You see that the thermal energy use is being reduced, but electricity is becoming also very important, and even more important than today, due to the fact that we are electrifying a number of end users. And on top of that, we are supplying a number of end users with hydrogen, e-gases, e-liquids, meaning that the total peak demand also will evolve and will increase quite substantially in these types of scenarios. Then in terms of heating, we have looked at 4 different sectors that are interconnected with the electricity system. The 4 sectors that are modeled are district heating for industries, district heating for buildings, on-site heat generation for industry, and on-site heat generation in buildings, collective heat or individual heat. The share of each energy sources is an input from the 1.5 tech scenario. And then what we have performed is to optimize the investment in CHPs and then compare it to the 1.5 tech scenario. So for example, on the left-hand side, you see final energy demand for space heating in buildings per energy. And you see in blue the 1.5 tech assumption, and then in orange the potential for optimized CHP. So in particular, we do not have competition between CHP and heat pumps in this scenario. We'll only look at the share of the heating demand that cannot be electrified. The integrated energy system scenario is defined as a variant of the 1.5 tech scenario, where we increase the share of thermal generation, biomass, biogas, and natural gas with CCS. We have a steady nuclear capacity installation rate comparable to current nuclear increase rate, resulting in a capacity of 50 gigawatts in 2050 compared with 120 gigawatts in the EU 1.5 tech scenario. So we have a larger share of biogas-based heat demand in district heating for buildings, also in line with increased biogas-based power generation. But the demand levels, electrification rates, and share of variable renewables is maintained as in the 1.5 tech scenario. And importantly, in this IES scenario variant, we also meet the net zero emissions objectives. So I'll now jump into the results for the system focus and then present the conclusions and recommendations. So in this system focus, we have compared, as I mentioned, we have provided the analysis for two different starting points, the 1.5 tech scenario and the IES scenario. So we have a range here on this slide where we provide the different benefits for CHP. So the range is due to the fact that we consider two scenarios. So in terms of energy cost, we see that we have a reduction of total energy cost of 4 to 8 billion euros per year at the European level, meaning that the additional investment in CHP is more than offset by the savings in terms of fuel costs and CO2 emissions. We have primary energy saving across the energy system of 150 to 220 terawatt hours per year. We have reduction of CO2 emissions by 4 to 5 megatons CO2. This is also due to the fact that even though we are in a carbon neutral scenario, we still have natural gas being used with CCS, but due to the efficiency of CCS, we still have emissions. So the more efficient use of natural gas or of gases can lead to a reduction in CO2 emissions. And then on the right-hand side of this slide, you have two figures that show the contribution of CHP in terms of total electricity. So 13 to 16% of total electricity. Here, the electricity, we only quote the part of the electricity that is connected to the electricity networks. There is a part of the renewable capacity that is connected directly to electrolyzers, so offsite, in order to provide hydrogen. So the 13 to 16% relate to the electricity that is connected to the network. And then in terms of total heat demand, we are between 19 and 27%, depending on the scenarios, and between 50 and 100% of thermal heat in buildings, industry, and district heating. So we'll now go through each of these benefits in turn, and we'll start with the savings in terms of investment savings and primary energy savings. So as I mentioned previously, we have found that there are savings between 4 and 8 billion euros per year overall at EU level. And here we have two figures on this slide that show the result for the 1.5 tech scenario on the left-hand side and the IES scenario variant on the right-hand side. So you see that there are additional investment costs in both situations, so meaning that there are these additional costs for CHPs, but the more efficient use of the fuels is more than offsetting this additional investment cost. And furthermore, there are CO2 emissions that are being saved, and using the CO2 cost in these CO2 price in these scenarios, these result also in benefits from a systems point of view. So again, between 4 for the 1.5 tech scenario and 8 in the IES scenario variant, billion euro savings per year at EU level. In terms of primary energy savings, we see that increasing the share of CHPs in all sectors leads to reduction of primary energy consumption at system level. And this is due to the reduction of generation of electricity from natural gas-fired units, thanks to better use of fuels. The savings are found to be around 150 to 220 terawatt hours per year, depending again on the scenario that is being considered. So on the left-hand side, you see the primary primary energy consumption in CHP and the savings in the other sectors. So you see, for example, for the 1.5 TEC scenario, that there are 465 terawatt hours of primary energy consumption by CHPs, but you decrease the consumption in the heat sector, in the power sector, by more than that, leading to a net decrease of 154 terawatt hours per year. And likewise, in the IES scenario variant, you have an increased consumption in the CHP sector due to CHP deployment, but this is more than offset thanks to the higher efficiency of CHPs in the heat sectors and power sectors. And on the right-hand side, I've just shown you in terms of fuels that are being saved due to the use of CHPs. In most cases, we found that natural gas is the fuel that we save thanks to the introduction of CHPs. And this will also be important then in terms of CO2 emissions reduction. So let's talk about CO2 emission savings. So here I've said in the introduction of the results section that between 3.8 and 5.5 megatons of CO2 savings can be generated annually thanks to the reduced use of natural gas in CCS plants, where we assume a 90% CO2 capture rate. In comparison, on the right-hand side, you see the emissions by sector in 2050 in the different pathways of the long-term strategy from the European Commission. And we see that in the 1.5 TEC scenario, there is still a little bit of emission at the 2050 level. And so in terms of comparison, these 3.8 and 5.5 megatons, they are about a fifth of the remaining emissions in the 1.5 TEC scenario. So really these hard to abate sectors can really be targeted with CHP and benefit from these emission savings. In terms of deployment of technologies, what do we see? We see that overall there are investments where we can add 86 to 96 gigawatts of CHPs compared to the 1.5 TEC scenario. Again, depending on the scenario, if we consider 1.5 TEC or IES, we have different numbers. So 86 for 1.5 TEC and 96 for IES scenario variant. And on the right-hand side, you see the impact in terms of deployment of the different technologies. So you have, for example, on the 1.5 TEC star scenario, CHP that increase in buildings quite a bit by 60 gigawatts, also in district heating and in industry. And then there are savings in terms of installation needs in heat production technologies, in gas-fired power plants, and in marginally in other technologies. And likewise, in the IES scenario variant, you see 96 gigawatts of CHP that are able to replace 13 gigawatts in heat production, 81 gigawatts of gas-fired power plants, and then marginal impacts on biomass and other technologies. So what does it mean in terms of heat production by sector? Here I've shown the results for the different sectors that we have mentioned that we are targeting in this study. So on-site buildings, industry, district heating for buildings, and industrial district heating. And on the right-hand side, you have this, this graph where we show in the total heat demand, what is the share being provided and supplied by CHPs. And for each of the sectors, you have two columns, the 1.5 TEC scenario from the Commission, directly from the Commission, and the optimized CHP deployment within the context of the 1.5 TEC scenario. And we see that the orange part, which is the one linked to CHPs, is increasing in all sectors in the optimal CHP deployment scenario. So we have more 236 terawatt hours of heat compared to CHP, to additional terawatt hours. We can repeat the same analysis in the IES scenario variant, and here we see that the results are even clearer, where we have an increasing share of the thermal heat production that can be covered by CHPs in all sectors, reaching more than 80% in industry and 70% in buildings. So CHP operations combine flexibility and efficiency. I think this has also been mentioned in the introduction. In the future, we'll have a lot of renewables in the system. We'll need flexibility on different timescales, and we'll need to have a system that adapts dynamically to the generation of renewables. So I have a few slides to show you how CHPs interact with other technologies from a heating perspective first, and then from electricity system perspective. So here you have a typical thermosensitive heat demand for buildings, and you have the demand, and this is the solid blue line, and then the contribution of CHPs and boilers on in different colors, so orange being CHPs and purple being boilers. And you see that during the winter time, when the demand is high electricity prices, CHPs are ramping up to cover the high demand and capturing the benefits linked with higher electricity prices. Whereas during the summer period, the CHP ramped down in response to lower electricity prices and lower demand. So you have a virtuous behavior of CHPs that really operate only when economic conditions are optimal for them to run. So it means mainly during the winter time, with small contributions also during shoulder seasons. And from the electricity system perspective, we have the same kind of graphs. We have 2 slides on this to illustrate the benefits in winter, summer, and then in periods with high renewable shares. So on this slide, we have the dispatch of different electricity generation technologies in order to meet the electricity demand. So the electricity demand is in the solid red line this time. And then we have stacked the different electricity generation technologies in order to meet the demand. So you have kind of base load renewables in brown, the solar in yellow. You have different offshore and onshore wind in green and blue. And CHP is the orange band that you see here. So here in the winter, you see that CHP run as a baseload during low wind and low sun periods, covering a high share of the peak demand in both these scenarios. In both scenarios. Here, I think it's for the 1.5 tech scenario that we show this analysis. So you see that they cover a large share of the demand in winter, and this is consistent with the picture I've shown you on the previous slide. In summertime, you see that here you have much more contributions from solar energy and from offshore and onshore during some days. And you see that the CHP production adapts dynamically to these periods. So in particular, CHP stops producing when variable renewable generation is sufficient to cover demand. And then CHP focuses on evening peaks in particular to meet the demand for electricity during these time periods. Then in terms of how it adapts in mid-season with high wind and winter with high wind, we see that on the left-hand side, we have a mid-season case with a relatively high wind production. And here we see that CHP function most of the time, but reduce generation also when solar production increases. So as you see that during the night, the production by CHP is much more important than during the day, showing how the CHP adapts dynamically to the changing conditions in terms of renewables. And again, on the right-hand side, here you see an episode in winter with relatively high demand, low solar availability, but high wind period. And here you see that CHP that continue to run across the entire period that we show, leading to enabling peakers to reduce their production first, because they are the least efficient technology in this period. So really, again, a virtuous behavior of CHPs in all these cases. So in terms of installed capacity, where does it lead us? It leads to an overall CHP capacity of around 142 to 154 gigawatts in the 1.5 TEC scenario and IES scenarios, compared to 117 gigawatts in 2018 and 56 gigawatts in the 1.5 TEC scenario. So here we have the CHP capacity per sector, both for the 1.5 TEC scenario and the IES scenario variant, where you see two columns, one for the baseline and one for the scenario where we have optimized the CHP uptake. So we see that in all sectors we have an increase of the deployment of CHPs in the optimal CHP deployment scenarios. In terms of the share of heat being delivered by CHP, we see that in all sectors in the EU, so here we have buildings, industry and cities, we have a large share of the total heat that is being covered by CHPs. So in terms of total heat, we have 26% in buildings. When we look at the share of thermal heat, we reach 52%. In the industries and SMEs, again, we have around 26% of total heat, but that amounts to 84% of thermal heat in this sector. And finally, in cities, we have about 40% of total heat that can be supplied by CHPs. But in terms of total heat production, this amounts to about 91%. So to recap on the key figures, we have seen that CHP can be a future-proof solution for 2050, since it has a number of different benefits. It's cost-effective. It brings benefits to all users in different sectors, as we have seen in the first user focus presentation of the results. It can reduce carbon emissions. It enables system integration, so it's a dynamic interlinkage between the heat, gas, and electricity systems. And it's an energy efficient solution that can be used to provide flexibility and to enhance the reliability of the energy system. In terms of primary energy savings, as we mentioned, we are between 154 and 221 terawatt hours, between 3.8 and 5.5 megatons of avoided CO2 emissions, and savings about 4 to 8 billion euros annually. So I will now provide key conclusions and recommendations in terms of modeling, and then I'll leave the floor for questions and comments. So as mentioned, both from the end user perspective and the systems perspective, we have found that CHP can be an efficient enabler for reaching 2050 carbon neutrality in a cost-effective way. So there is indeed a more cost-effective potential for CHP to tap into to support a highly electrified and low-demand energy system compared to the 1.5 TEC scenario. And in the scenario variant, the IES scenario, where we have a higher uptake of bioenergy sources, the deployment of CHP that we have found is even more important and enabling an efficient use of the fuels produced either via biomethane or e-gases. The optimal CHP deployment leads to a reduced system cost and CO2 emissions, as mentioned previously. They can displace less efficient power-only and heat-only generation technologies reaching up to 30 to 36% of thermal power and 50 to 100% of thermal heat production in 2050. They, of course, are a solution that maximize system and resource efficiency and provide flexibility to the power system. And we have found that CHPs can be relevant in all sectors of the economy, buildings and industry, either on-site or when connected to district heating. Of course, for this potential to materialize, we have to ensure that there are no barriers that prevent CHPs and in general the most cost competitive solutions to deploy. So here we see that the benefits of CHP are quite wide in terms of the origin of these savings. They allow to save some CO2 emissions, some investments in other technologies, and some operational costs. So the market structure and the regulatory regime at the national and European levels should allow CHP to capture all the value that they bring to the heat and power system in terms of also of avoided network costs and generation capacity. Currently, the revenues of CHP can be scattered across different markets, some being country-specific. The taxes and the tariffs may not always provide the appropriate price signals, so we have to ensure that they do in order that the most cost-effective solution from a system point of view integrate the system. And in many cases, the value that CHP brings in terms of avoidance of electricity network reinforcement cannot be captured by the CHP owner. So this is one barrier that has been identified and should be worked on. I think Hans will also provide some recommendations on this. And finally, as we have seen, CHP can contribute to meeting peak load by adapting the way it behaves in the electricity system. So it means that it should be able to capture the corresponding revenues in case capacity remuneration mechanisms are put in place. And finally, in terms of recommendations on modeling, we've seen that we have been able to identify a number of applications and deployment of CHPs that go beyond what has been considered in the European Commission scenarios. And we think that in order to identify these potentials, it is essential that we use models that jointly consider the power system, the heat system, and the gas also, with an adequate level of details in terms of representation of the heating demand in particular for different temperatures, different technologies that can provide heating for different temperature levels. The CHP operation should be modeled to complement variable renewable generation by adopting cost-efficient operational management of the system. So here the market model that we have used in this study, Artelys Crystal Supergrid or METIS, that is the configuration that we have delivered to the European Commission, could be used for this purpose. The heat consumption should be modeled, as I mentioned previously, with sufficient details in each country by heat sectors, so buildings, industry, district heating, and with different temperature levels. This is important in order to represent the competition between the different alternative technology packages. And again, the diversity of heat supply solutions should be accounted for in each sector. And we have seen that in the analysis of use cases that there are different CHP technologies that can be relevant in each of the use cases. And finally, I think an important point in terms of studies and upcoming modeling exercises, we have found that it is important that we are able to capture the benefits of distributed electricity generation in terms of avoided distribution network reinforcement costs and avoided electricity losses. So an effort in this area is important in order to help identify the optimal deployment of CHP technologies. So with that, I thank you very much for your attention and happy to take some questions together with my colleagues that should be on the call with me.
Thank you, Christopher. Thank you very much. That was a substantial body of work and an excellent presentation. You have certainly sparked a lot of interest in questions and comments. I'm going to run through them, and then yourself or your colleagues, Maxime and Anthony, can chime in. Some are very simple, just clarifications, and I'll start with some of the simple ones, and we'll get into some of the more meat as we progress. We have about 20 minutes to do a Q&A session before I have to wrap things up. So first question, what do you include in the green gas category, both renewable methane and renewable hydrogen? These are, go ahead.
Yeah, exactly. We in this study we have indeed considered, so biomethane is one of the green gases that will become that is considered in the study, but also the hydrogen, especially hydrogen in the study where that is produced via electrolysis. So we've seen in the 1.5 TEC scenario that there is substantial growth in the renewable sector, and part of this growth is due to the fact that we have to provide enough electricity in order to produce that hydrogen that can then be also transformed into e-gases.
Thank you. And I guess linked to that as well, there was a question regarding the fuel source and the comparison between boiler and CHP, and if you can, what price did you use?
So for almost all the assumptions, we have used the prices that are published in the 1.5 TEC scenarios, so that we have a comparable basis with the scenarios of the Commission. I don't have all the numbers on top of my head, but they will be published with the study. So there are ample analysis provided in addition to these slides, where we have referred to all the assumptions. And if my colleagues want to jump in, don't hesitate.
Just as a reminder to everyone, we will make these slides, both the Artelys slides as well as Cogen Europe's slides, available up to the presentation, so everyone can dive into the finer details to see if they can find a question. The next question here, under the use focus, do you mean green gases for engines? And are these engines using hydrogen gas or other gases, assuming not natural gas? As this is looking at 2050, obviously we're looking at a net carbon neutral system, but you can answer in more detail, of course.
Yeah, I think you have provided the answer here. We can see the different configurations that we have used. So indeed, we have green gases for the different use cases. For the fuel cell, also we have different sensitivity analysis depending on hydrogen prices, and here too hydrogen produced via electrolysis. Indeed.
Okay. So based on these results, how do you expect the business models for various CHP applications to change by 2050?
Yeah, so I can start an answer. So here we see that indeed, I think one important result is that we have found that deployment of CHPs is economic in all the end use that we have considered and in all the sectors that we have considered in the system level analysis. Of course, there will be there might be some changes in the way CHPs are being operated. We have seen that in order to complement renewables, we have not assumed that there is a kind of a base load way of operating CHPs. So here we have seen in a number of different cases that a virtuous way of operating CHPs will be complementing renewables, and I think that in other sectors, especially in industry, there might be some areas where other ways of operating CHP will still be relevant. But I think one of the key points to take into account is this more interlinked way of operating CHPs. I'll let you perhaps complement, or if you have other aspects of that question that you would like me to address, just let me know.
Okay, thank you, Christopher. Another, just running through, there's quite a few questions here. How can you run CHP economically when the e-production is higher than demand? A simple economics question.
So could you just repeat that? I didn't get it.
Yeah, how can CHP run economically in 2050 when the production of e-gases is higher than demand?
So here we have okay. So in all these scenarios, we have the production of CHPs adapts dynamically to the situation in terms of electricity demand. So indeed, we have a situation where the entire scenario, the 1.5 tech scenario or the IES scenario, is dimensioned in a way so as to be able to produce at the same time electricity to supply the electricity demand, the final use of electricity, but also the demand for e-gases. So there will be periods where there will be a lot of periods where you have excess of electricity compared to the final electricity demand. During these periods, you'll have electrolyzers running, and then you have storage that can be used to then supply green gases back into CHPs. So and here, perhaps one important point is that the figures that I've been showing today in terms of these dispatch figures are only for one country. So it might be the case that in a given country you still need to have CHP running during high res production within that country in order to supply a neighboring country and avoid more carbon intensive or more expensive fuels being used in another country, in a neighboring country.
Okay, thank you. Just bear with me. Yeah, how will CHP be fueled in a carbon neutral energy system? I think you've answered that question. Yeah, is the analysis also available per member state, taking into account specific local factors such as power groups and gas prices and grids? So
we have performed the user focus analysis for 3 archetypes for different countries. So for these analysis, we provide the results for the 3 archetypes. For the focus on the system level, we provide results at the European scale. But the analysis has been performed with a member state granularity, adding also the neighboring countries, of course.
Thank you. Another one. With the greening of electricity generation sector, does CHP still offer CO2 reduction for customers in the UK? That's very specific, but maybe generally speaking.
Yeah, so here again, I cannot comment specifically on the UK case. I don't have the figures on top of my head, but but indeed the point here is that in this scenario we have periods where there is simultaneous use of electricity generation and heat provision, and so using the most cost efficient and efficient technology on the market can really help you reduce the remaining CO2 emissions. In particular, if you reduce the use of natural gas-fired power plants that are equipped with CCS, because the capture rate of these plants is not 100%. So you save these emissions.
Okay, thank you, Christopher. Another question here. How can CHP be better accounted for its reductions of grid losses?
So I think there is, so on our side, we have taken into account additional benefits of CHPs by performing a literature review of a number of different articles in the literature to see how to account for reduced grid losses by adapting the efficiency of CHPs. Of course, this is a kind of an implicit way of taking into account that phenomenon. But more in general, I think that in order to understand the reduced grid losses and the avoided investment in networks, you would need to go to a refined modeling of the networks themselves and to see how the operations of CHP can impact the flows on such simulations, and then to assess the benefits from there. Of course, this was not within the scope of this study, but we have taken both phenomena implicitly into account based on a survey of the literature.
Thank you. We have time for a few more questions. Actually, you've stopped on the right slide at least. How can seasonal peak demand be mitigated? Is CHP necessary, or how can it be addressed via demand response and heat power storage alone?
Yeah, so indeed, providing flexibility in these high renewable scenarios is one of the key issues, and flexibility has to be provided on all timescales. So here we do not have, I don't have a slide where I show the way the different technologies combine to provide flexibility on all those time frames. But indeed, we see that from the analysis here on this slide, during the summer, you see that CHP has quite some flexibility on the daily timescale. We've seen on this slide that CHPs can also adapt during periods with high wind periods, and then can reduce their consumption during other periods, depending on the deployment, on the production of renewables. Meaning that they can also have this kind of flexibility, what we call weekly flexibility. And then finally, in terms of providing flexibility on the seasonal scale, they combine with other technologies in order to provide that flexibility. We've seen in the figure here that focuses on heat generation for a particular sector, that they will provide an output only during, in this application, specifically during winter time and not really during the summer. But in terms of the total need for seasonal flexibility, I don't have a figure here, but we see in all the studies that we have run that all technology combine to provide this flexibility, including electrolyzers, including hydropower and electricity interconnection, the gas system more in general too.
Okay, thank you, Christopher. Well, a technical question regarding your scenarios and calculations and modeling. Are climate neutral fuels for CHP in 2050 just gases, or do you count on other climate neutral liquids as well, biofuels, liquid e-fuels, etc.?
So here in the cases that we have considered here, I'm just going to go back to the end use cases. Here we have gases, and in the last use case, you see biomass fluidized bubbling bed CHP. So these are the fuels that we have considered for the user focus. So mostly green gas engines or turbines and fuel cells also with hydrogen.
Okay, thank you. I think maybe one more question. Let's see. How does CHP complement end use and system level electrification? Do you see CHP and heat pumps competing or complementing each other?
So here in this study, it's pretty clear that they complement each other. What we have looked at is in the 1.5 TEC scenario, there is a demand for heating, and we have separated it in different levels of heating temperature. There is a part of this heat that can be delivered by heat pumps, and part of this heat that cannot be electrified in a direct way. So it is this part of the heating demand that we have analyzed more in details, where we looked at the trade-off between investing in CHP and alternative technologies. And the outcome of the analysis is that in order to provide that heat that cannot be directly electrified, CHPs are the most cost-efficient technology that is available, thus leading to the higher deployment rates that we see in our results compared to scenarios that are based on the 1.5 TEC scenario directly.
All right, thank you, Christopher. We're getting to the end of the webinar, so I'd like to thank you again for your presentation and for you and the team to join us to ask the questions. We had over 50 different questions. Unfortunately, we didn't have time to get to all of them, but we will take note and see if we can get back to the different individuals separately via the Cogen Europe team. So I'd like to use these last few minutes, if I may, to present a very short presentation. I will focus, if you bear with me 1 second. Here we go. So yes, as said, I'll provide a wrap up, a summary. Some of these things you have seen before in one form or another, but I think it's important to reinforce some of the main results. But to start, as mentioned by our chair at the start of the webinar, in 2018, our organization, 1 second, something is flashing on my screen. Apologies. Yes, as mentioned by our chair at the start of the webinar, in 2018, our sector adopted a new vision for the future, and this vision was supported by over 60 different members spanning the entire value chain. The vision outlines our sector cogeneration commitment to creating a resilient, decentralized, and carbon neutral energy system by 2050, where cogeneration is at its backbone. Cogeneration is a key enabler to achieve carbon neutrality in Europe by 2050 by prioritizing CHP for thermally generated heat and power in all sectors. Will maximize the energy efficiency and integration of the energy system at least cost. Our study was supported by prominent players in the whole energy value chain with an interest in cogeneration from technology manufacturers, users, utilities, energy service companies, consultancies, and national cogeneration associations. Most of them are Cogen Europe members, but other organizations outside the membership also supported this important piece of work, this large body of studies. So I'd like to take this opportunity to thank all the different partners for their support over this entire process. Just quickly, I mean, as an overview and a summary, the study demonstrates the benefits of optimizing further deployment of cogeneration in both scenarios in all sectors to reach higher system cost savings, primary energy savings, and CO2 reductions. And this is compared to the European Commission's long-term strategy projections. I'm not going to go through each detail, but you saw that you see cost reduction for energy system between 4 and 8 billion. In terms of the remaining CO2 that you have in 2050, CHP can contribute to a reduction of another 20% of the remaining emissions. In terms of, heat, the study also shows that in 2050, CHP brings end user benefits and is well suited for all sectors, including the domestic sector, and we're talking about 20% of total heat and 52% of thermal heat. Looking at industry and SMEs, 26% of total heat and 84% of thermal heat. So these are significant figures. Another key learning is that the study demonstrates the critical role of cogeneration to support a highly renewable and electrified system. So CHP operations can be optimized to reliably and flexibly respond to power market prices and heat demand, but CHP does not compete, but complements variable renewable electricity generation. As such, CHP is a flexible solution alongside batteries, hydro storage, and demand-side management to meet electrical system needs. It's also important to understand that CHP's short-term flexibility will vary by application, heat or power driven. There are significant cost savings for CHP users. Obviously, it depends on where you are geographically, weather, resources available, etc. But you can see savings for district heating, use case using a hospital as an example, in industry in regards to high temperature, but also medium temperature industry, and even including industry and city district heat. You have ranges between 1.4 or 400,000 and 3 million from a district heating perspective, all the way up to 16 million in some cases. And the examples are, for industry high temperature heat, it could be a chemical plant, it can be an alumina plant. In terms of median temperature in industry, we're talking about the food and drink industry. There are many different applications. CHP is a future-proof solution for 2050, and it brings key benefits to all sectors. CHP is a resource efficient and energy efficient, avoiding the waste of valuable resources. CHP helps reduce remaining CO2 in a carbon neutral energy system. CHP is cost-saving solution. CHP is also critical for highly renewable and electrified energy system. CHP also enables the integration of the energy system by linking electricity, heat, and gas at a local level and providing energy when and where needed. And my next slide will provide that illustration. And finally, CHP brings end user key benefits and is well suited for all sectors in terms of buildings, commercial, district heating, and industrial. So here's a very good example of system integration. CHP enables an integrated energy system by linking things like electricity, heat, and gas at a local level and provides energy when and where needed. So CHP will enhance the reliability, but also the flexibility of renewable-based and highly electrified and integrated energy system. As we see it as the most energy efficient solution among different thermal energy generators, CHP not only reduces the use of fossil fuels, but is the best solution to support the system based on renewable energy and contributes to system resilience. It also brings together the heat, the electricity, and gas networks together to ensure the most efficient energy conversion among them. That's why we see CHP as a backbone to this future energy system. So as predicted in future energy scenarios, the role of electrification is due to increase, and CHP will be important in delivering efficient electricity locally when and where it is needed. Finally, there is an important cost-effective potential for highly efficient cogeneration in the 2050 carbon neutral system. Today, CHP provides 11% of electricity in Europe and 15% of the heat in Europe. We have extrapolated already in various different co-funded EU studies that the share of electricity can be doubled by 2030 with the right policies in place, and can provide up to 25% of heat in Europe with the right policies and incentives in place. And in looking towards 2050, based on the modeling, we can see that in addition to what is already installed today, there can be an additional 40 gigawatt more installed for CHP in the 2050 system. And that's actually more than two and a half the capacity that was projected in the Commission's 1.5 tech in the long-term strategy. 20 gigawatts is not insignificant. It's the equivalent of 40 nuclear power plants, 1,000 megawatt nuclear power plants. Today in Europe, you already have 107 nuclear power plants in Europe, to put things into perspective. And then finally, in terms of policy recommendations, in particular the European Commission, the European Parliament, but also member states, what we're saying is that we need to fully recognize CHP's role in sectoral policy for industry, buildings, and district heating. We need to better account for CHP displacing less efficient and more carbon-intensive marginal generation. today and all the way up into 2050. We need to foster CHP to deliver the lowest cost heat and better valorize waste heat. And this applies to everything that we're discussing today, the European Green Deal, the different strategies that were published by the European Commission. It could be the industrial strategy, the renovation wave, but also the work that's already begun in terms of revising the existing legislation in terms of the Energy Efficiency Directive, the Renewable Energy Directive, but even more specific things like energy labeling and eco-design. This will be my last slide in terms of policy recommendations. We need to make sure that CHP is rewarded for its positive impact on system efficiency. Better consider the role of CHP to integrate heat, power, and gas systems in a flexible and efficient way at a local level. So energy system integration will be key here. We need to get the right structure and policy framework in place. And then finally, we need to foster a predictable policy framework towards carbon neutrality. We can't keep on changing legislation retroactively. We need a predictable framework in order to make the right investments to maintain the existing capacity in place, plus the additional capacity that will be needed in terms of how we see CHP supporting a net carbon neutral system in 2050. So that is it from my side in terms of the wrap up. We're just a few minutes over time. So I'd like just to thank everyone, but in particular Christopher for joining us this afternoon and presenting the results of the study. And also thank you to Maxime and Anthony and their patience over the many months of work with Artelys to get the results in place and to be in a position to present these results to you all today. Thank you to our chair, Marco, for joining us and supporting today's webinar, and also a special thanks to the European Commission for joining us at the beginning to provide their perspective and reinforce the importance of getting the European Green Deal right, and also addressing how CHP can support that moving forward. So I'd like to thank the plus minus 200 participants that chimed in and out of today's webinar. As I mentioned at the beginning, the webinar was recorded, so it will be available online via the Cogen Europe website. All those of you that registered, we have your contact details, and we will let you know when everything is ready. So thank you again, everyone. Thank you for participating. Thank you for taking the time during your lunch, whatever. We appreciate it, and we look forward to continuing to share the results further and different fora and different means. So with that said, on behalf of the Cogen Europe team, whom you don't see, but certainly was very valuable in bringing this all together and bringing us to a position where we can present that to all of you. They worked tirelessly with the Artelys team to get us here today, and so without them, we wouldn't be ready. So thank you. Good afternoon. I wish you all a pleasant end of the day.